So we're going to review kinetics, and again, this whole review packet is in your review tab on Edline. I would definitely look this over before any weekend assignment, before any mock exam, etc. On page 15, you've got kinetics. There are a number of factors that affect reaction rate. You always want to explain it through the collision theory, and keep in mind any factor that increases the likelihood of an effective collision will increase the reaction rate. With that said, two factors there. You want to make sure that the molecules hit one another hard enough to overcome the activation energy barrier. Make sure you indicate to overcome the activation energy barrier. That is, climb over that hill to go from reactants to products. We'll point that out in just a sec. And the other thing is you want the molecules to be oriented properly, because if the right atoms within the molecules don't collide with one another, regardless of the force, you will not get an effective collision. Anything that increases the likelihood of an effective collision will increase reaction rate. The factors you want to consider are concentration. You can look at that in regard to a rate law. A rate law is different from a rate equation. A rate law only has reactants in it and also has Ks. Those are determined from experimental data and mechanisms, not from balanced chemical equations that aren't in mechanisms, that are in elementary steps. Temperature is another factor that affects reaction rate, and we've looked at this in regard to Maxwell-Boltzmann. Previously, we looked at it in the gas chapter. We've got two curves here. The one at the higher temperature is T1. We talked about the curve moving to the right at higher temperature and being smushed down. Here's the activation energy, the minimum amount of energy required for the reaction to occur. This is a barrier, if you will, from reactant energy to product energy, and you can see here that more molecules will have enough energy to overcome the activation energy at the higher temperature. And you've seen a lot of these types of multiple choice questions, know how to manipulate that curve. As you increase temperature, you slide to the right and you smush down. The area under both curves would be the same. In regard to the collision theory, a lot of that is indicated here. I won't go through every single step, as we just want to review a few key concepts. Catalysts are substances that increase the reaction rate by providing an alternative pathway that has a lower activation energy. The catalyst is not consumed during the reaction. In a reaction mechanism, the catalyst will be a reactant in one elementary step and a product in a subsequent step. A reaction intermediate crisscrosses the other way, where it is a product in an elementary step and a reactant in a subsequent step. Surface area is a key point as well. When you compare solids with powders, powders have greater surface area. They have more sites with which an effective collision can occur. Anything that increases the likelihood of an effective collision will increase reaction rate, and that's what you were looking at with your quiz. Make sure you know the difference between rate equations. Rate equations are where you take the stoichiometric coefficients into account. You have rates, that is concentration per time. You can have reactants and or products. With reactants, you've got -1. With products, you've got +1. Rate laws have only concentrations of reactants only, and they are raised to some power n, m, maybe l. The overall order is the sum of the exponents, and remember the units for your proportionality constant, k, that is lowercase k, that is m, that is molarity, 1 minus overall order, OO overall order, time to the -1. So if you had a first order reaction, M, 1 minus 1 would be 0. Anything to the 0 power is 1 time to the -1. So if you had first order, it would just be time to the -1, such as minutes to the -1 or seconds to the -1. If you had a second order reaction, you'd have 1 minus 2 is -1, m to the -1, time to the -1. Be comfortable with units for K, very often comes up. I'm not going to worry about instantaneous rates right now. And this particular chart will help you as well. I'm going to shrink it slightly. This is in your notes. It's here. And this is what's going to help you determine from a plot whether you have 0 first or second order. So if you have concentration only on the y-axis versus time, and you have a straight line graph, that's that top panel here with a negative slope. Maybe not. That's when you've got 0 order. That's not that common. If you have 0 order, altering the concentration has no effect on the rate because the concentration is not in the rate law. The rate law is equal to K only. So you've got that right here. Here's first order where you have ln of the concentration of reactant versus time. And again, straight line kinetics where slope is equal to -K. And here what you've got is 1 over the concentration of the substance versus time. This is going to be second order where you have a positive slope equal to K. This is a little more involved than what you need, and it also looks like there's a typo right here. This should be a 2 here. Sometimes this is very tricky to alter. I'll try and plug it in, and there you go. So I'm not sure what happened to the 2 there. That's important. Make sure you make the change. I'll update. So that's second order as opposed to a first order rate law and a 0 order. So if you are given this plot only, you should be able to write the rate law. You can be given lots of plots, but only the straight line illustrates the order. Straight line where you've got that as your y-axis would be second order. They give you a lot of what is up here, so be comfortable with that. They don't give you the 0 order, so you don't need to know it. They give you this, and they also give you this formula right here where the half-life for a first order reaction is 0.693 over K. So if they give you the half-life and you know you have a first order and you're asking for K, K would be equal to 0.693 over the half-life. So you could work it that way. In regard to your mechanisms, be comfortable with a few things here. For example, let me blow that a little bit so you can see. Sometimes they ask you the molecularity of the reaction. You've got a unimolecular reaction here, 1 reactant with a coefficient of 1. This is a fast equilibrium step. These are bimolecular right here because you have 2 reactants, both with coefficients of 1. If you catalyze it, for example, by throwing in palladium, you'll get the reaction to occur at a faster rate because you've provided an alternative pathway with a lower activation energy, and that's what's shown here. You've got a lower activation energy there due to the catalyst. You can see it here as well. Keep in mind on the left you've got an endothermic reaction where the product will be greater than the reactant, hence a positive delta H. You can see the activation energy, and this is important as well. Always from reactant to the tippy top. Always from reactant to the tippy top. In an exothermic reaction, delta H is going to be negative, again, from reactant to the tippy top for activation energy. This might be where you have a catalyst, where you have an alternative reaction mechanism, where you've got a lower activation energy, so more molecules can overcome, thus increasing the reaction rate. So you've got endo versus exo, and those are the key things there. You want to be comfortable with this. There's a lot more to this that we've talked about previously, and make sure if they ask you to draw the activation energy in, you do it for the rate determining step. Why would you do it there? What determines the overall rate of the reaction? The slow step, which is the rate determining step. That's the one that's going to determine how fast something occurs. If you go into, I don't know, where do you like to eat? Let's say you're going to Chick-fil-A and you want to get your sandwich and now you want one without pickles, so now you have to wait. So the slow step is how fast they can make that new sandwich, and then you'll be on your merry way. All right, I was looking. I just want to focus on one easy thing here, and then we'll take a look at this other exam, and hopefully that will help you with a few concepts. Will you have kinetics mastered after this? No, but if you spend some time tonight, then you probably will have it down, such that when you start to review big time, it's just a matter of digesting a few things rather than, oh my gosh, I can't remember anything. All right, this was off the 2012 exam, and these are all on AP Central. This was still the old exam, but they were bridging to the new exam, and you'll see it. It says an experiment is carried out to measure the rate of the reaction, which is first order. Okay. They show you the reaction right there. I'm going to scribble that down for a sec. So you would have had C2H5NH2 generating C2H4 and ammonia. And this is actually a really nice question, and it's somewhat similar to what you'll see on the 2017 from last year. This is the 2012, and I mention it because you're going to hit your weekend assignment. But one of the other things they ask for in this question is to calculate delta H based on bond energy. And please remember that if you're calculating delta H based on bond energy, this is the one and only time that you'll do reactants minus products. And this was on last year's exam. And I was looking over some of the booklets, and a kid who got a 5 did it backward. But he followed his answer through, so he just lost the 1 point there. This is the one time you'll do reactants minus products if you've got bond energies. If you've got delta H as a formation, you do products minus reactants. And that happens to fit in this question, which might be a good idea to look at as well. In any event, they asked for the rate law, and they told us first order. So what would the rate law be? Every rate law has what in it? K, lowercase k. Now we've got the concentration. Is it reactant or product? It better be reactant. Raised to what power? The first, because it's first order. You wouldn't have to put the 1. So that would get you a point right there, if that's what was asked. If they asked you for the units of K, what would that be? We know it's M, 1 minus overall order, time to the negative 1. 1 minus 1 is 0, so there's not going to be molarity here. It would just be time to the negative 1. And they had given some information saying time was minutes, so the units here would be minutes to the negative 1. Now what they actually asked in D&E was a little challenging, probably more than we want to hit right here. We can come back to it because I have a question that I think is quite nice and reasonable to do in the allotted time. Question F. says, if 1 over the concentration of ethylamine is plotted versus time for the reaction, would the plot result in a straight line or would it result in a curve? Explain your reasoning.
So it's actually it's second or third order.
Well, you know it's first order.
So therefore it's not straight, right?
Why? So they're saying, would 1 over the concentration of ethylamine versus time yield a straight line plot or a curve?
Yeah, a curve because it'd be straight line under second order reaction graph.
Absolutely. It would be a curve because the only way to get a straight line for this versus this would be if it's second order and we had been told it's first order, and that's sufficient. If you wanted to get a straight line, what would you have plotted? ln of the concentration versus time. Very easy question in terms of part F. The other parts of the question were a little bit more challenging. We can come back to that. What I really thought might be worth taking a look at.
Okay.
Yep.
Isn't natural log the same thing as what you do? Like natural log of 52 divided by
No. The way to get a straight line for first order would be ln
I'll say the calculus.
versus time. That would give you straight line kinetics. That is not equal to that.
I'll say the calculus because the derivative of that would be that into.
It is? I don't think so.
That would be 1 over.
If you had, let's say that the concentration of this is that. The ln of it versus 1 over the concentration. Let's take a look. I'm pretty sure it's not. My calculus is old, but no way. So if you had ln of 0.01, that would be this. And if you had 1 divided by that, the reciprocal, you'd have that. So
I was thinking the derivative, which is kind of irrelevant and stupid. So,
no, you're fine. But it's not. All right? So this gives rise to 0 first or second order if it's straight line. First order with a positive or negative slope. Negative. And in regard to slope, you know, like an n in negative slope. All right. Taking a look at this question, and I just want to focus on, we can do all of it, but I think we'll focus on the latter half initially, and then if we have time, we'll work our way backward. This is before the longies and the shorties, so this is sort of a medium type question. This was one of the older exams. This is the last old exam, actually. It says a sample of ethene is placed in a previously evacuated rigid 2-liter container and heated from 300 Kelvin to 450 Kelvin. The pressure of the sample is measured and plotted in the graph below. So you can see here as temperature increases, what happens to the pressure? It increases as well. I'm going to work this one a little bit backward. I want to focus on the reaction mechanism piece here. It says, it is proposed that the formation of ethyl chloride proceeds via the following 2-step reaction mechanism. Here's step 1, here's step 2. And I can make that a little bit bigger. Take a minute. You need it bigger? take a minute to do C and D. Give it a shot. Should be able to do it.
It says identify something in the definition. Do you want us to explain it as well?
No, it doesn't say explain, don't waste time. ID means ID. Did you get this? And you could have either of these. Yes, yes? So would this be first or second order? Second is correct. Okay, the other part of the question here, I'm going to have to go a little smaller so you can see it. It says, using the axes provided, draw a curve that shows the energy changes that occur during the progress of the reaction. The curve should illustrate both the two-step mechanism and the enthalpy change of the reaction. You also want to indicate the activation energy.
Is the slow step the highest?
Well, I'm not going to answer that because you're going to answer that. And I'm just wondering, right here is your value for delta H. So assess what's important in regard to that delta H value. So you've got what's pertinent there and draw that curve. Ready? I would have done this. Is that what you did? So you are correct. The rate determining step would be the high one. The activation energy is from reactant energy to the tippy top. I'm not sure I'm actually at the tippy top of that mound. I'm going in at an angle, so if it's not perfect, I apologize. And then it indicated that the reaction was in fact exothermic. Let's take a look at one other thing here, because even though we're doing kinetics, I really feel like the linkage is so critical at this time of the year. they told us that the reaction was exothermic. Is this reaction illustrating order or disorder? Why? Because the number of moles of gas is decreasing from reactant to product. 2 moles of gaseous reactant, 1 mole of gaseous product. And because this is going toward order, delta S would be? Negative is correct. So from that information, you would need to know about the temperature to figure out if that reaction was thermodynamically favorable. Questions there? Okay. If you would like, it might be very helpful to you to try A and B. Give it a shot. Can I who? Oh, yeah. Move my head. And we'll work through these answers. A and B done? Not quite? And we can actually go right off the scoring guidelines here, and we can explain it in more detail if necessary. So what you're looking for in A, provide 2 reasons why the pressure changes as the temperature increases. Your descriptions must be in terms of what occurs at the molecular level. You know as you increase temperature, the particles are going to move at a faster rate, and that will lead to more collisions. In addition, as the temperature increases, we know average kinetic energy increases, and so you will strike the walls of the container with greater force. And we've talked about that previously. In the other question, you can see 2 moles of gaseous reactant to 1 mole of gaseous product. When HCl is injected into the container that contains ethene, the total pressure increases. Then as the reaction proceeds in the forward direction, the pressure is going to decrease. Explain this decrease in total pressure in terms of what occurs in at the molecular level. And what you're looking at here is you have 2 moles of gaseous reactant, you generate 1 mole. You know moles and pressure are directly related based on PV equals nRT. As you generate 1 mole of gas compared to the 2 moles of gas you started with, you have a decrease in moles, hence a decrease in pressure. It says when fewer gas molecules collide, due to fewer being present, you're going to get a decrease in pressure. And in regard to the rest of the question, and we did this one a little bit backwards, you can see that these were worth a point as well, and we were very successful here with labeling it up. And that's your AB. So I hope just a little bit in regard to kinetics helped. You still have a few minutes. If you have any questions, we can address them. But again, if you will pick a concept tonight and look over that review sheet, and if you want to know what type of questions go with it, I'd be happy to tell you.